Hi, so in this video, we'll talk about the convergence of a series that's defined differently for even and for odd terms. So this looks like it's going to be a little bit complicated. It's at least not in the simple ones that show up in the first example of a book. So first of all, let's look at what this looks like. So it has a different definition if this is like if n is odd versus it's even. So what does that mean? That means that this looks like the sum of the n's that I'm looking for. Uh, if the first term is 1, right, starting from 1, so n equals 1 gives me the odd, so it's 1 over 2 to the 1. And then I go with an even rule, which is this one. It's going to be 1 over 2 to the 2. Then I'm going to go to the odd again. So I'm the third term, right? This is n equals 1. N equals 2. I'm going to write n equals 3. So it's going to be a 3 divided by 2 to the 3, and so on. So for n equals 4, I'm back to the evens. So it's 1 over 2 to the 4. Let me just write one more. When n equals 5, this looks like 5, sorry. 5 over 2, over 2 to the 5. Okay, so I'm going to stop there and just put these points. So this looks like 1/2 plus a quarter plus 3/8 plus 1/16 plus 5 over 32. So it's a little bit getting out of control, and they're not suddenly getting smaller. 3/8 is a little bit smaller than 1/4. No, it's bigger than 1/4, right? So this term is bigger than that term. They are getting smaller as all, but you have to think about a way to manage this. So how are we going to do this? Well, the key point is that what both parts have in common is that both have a 2 to the power of n. And we already seen at this point the root test, which just means, so the root test says that you take the limit when n goes to infinity of the nth root of the absolute value of your terms, and you call that L, and if L is less than 1, the series converges, and if L is less than 1, diverges. So let's find out what we can do without this one. So and again, the key point here is that although it's defined in pieces, both parts have a power of n right there, right? So if I take the root, if I take who the hell is the nth root of the an term, I don't need the absolute values here, but let me just try that. So it's defined in pieces again, so let me write this down. So if n is odd, I would be dealing with the nth root of this term, right? So I will be doing the nth root of n divided by 2. And if n is even, I'll be dealing with only 1/2, right? Because I'm taking the nth root of this term. So the nth root of that term becomes this, and the nth root of this term becomes that. Okay, if n is even. Now, something to notice now that we have these is that all we have to look at this carefully is that the nth root of an, I'm not going to put the absolute values now since we don't need them, they're positives, is always bigger than 1/2 or equal, because this term here is really 1/2 times the nth root of n, and then it's going to be bigger than 1, so the nth root of n is going to be bigger than 1. So this quantity is bigger than 1/2. Okay. And we found already our Well, this term, we've been working with this term a few times by now. If you don't remember, go back to the video before this one when we talk about the root test and we took this limit again when n goes to infinity. This guy we saw already a few times, that the limit when n goes to infinity of the nth root of n is 1. The trick was to take the natural log, take the b and the natural log of this one, take the limit of that one, you get 0. So we want to get back to this one, it's e to the 0, so it's a 1. So there you go. With this argument, we can see that this sequence converges to 1/2. It gets squeezed between 1/2. So using the squeeze theorem or sandwich theorem, using the squeeze theorem, the limit when n goes to infinity of the nth root of an is less than the limit when n goes to infinity of 1/2 times the nth root of n. And then this side there was a 1, there was a constant, so this has to be 1. Sorry, this term is 1 times 1/2, so the limit that I'm looking for is 1/2. So then we got our L. My L is 1, so I'm in this case, and the series converges. Okay, so something to be mindful about what's going on here. I know that what gets confusing is that up here we're talking about the series to converge. To see that the series converges, the root test converts that argument into decide if a sequence converges. Okay, and then right now we're just doing that the sequence converges to 1/2, and that's enough to say that we're right here, so the series converges. Okay, so this is a convergence series. Okay, I hope that was a good example to talk about these.